So we're Team NewAJe. We competed in the 2024 RoboCup Rescue Simulation competition at the Eindhoven, Netherlands. I'm Etaash. I'm currently a senior at Montgomery High School, and I worked on the build system for our code, the UI, and also our mapping algorithm.
I'm Jiachen. I'm a junior at Hillsborough High School, and I work mostly on navigation.
I'm Andrew. I'm a junior at Princeton Day School. I worked on the map bonus.
Alright, so we'll just go over what the competition is, the design of our robot, how we did our LiDAR mapping code, and then our navigation algorithms. Then we'll go over our victim and hazard detection code, then finally map bonus and our technical challenge round.
So first, a little bit about the simulation we used. We used WeBots, which is a multi-purpose robot simulator, and we used the 2023B version. And it's used to render the robot and the mazes and to simulate the runs. And for RoboCupJunior specifically, Erebus is the supervisor that controls and scores all our runs. And on the window, you can see up there, you can upload your robot file and your code. The code can either be in the form of an executable file or a Docker container. Docker is a tool which allows code to be run on various environments, and we use C++ to code a robot, and we built it with CMake, so it can be run.
Yeah, so we are NewAJe, and the world is a maze with 4 different rooms with different conditions surrounding the environment. The goal is to detect hazards and victims on walls to get as many points as possible. After we finish exploring the maze, we return to the start to get an exit bonus, and the supervisor scores everything, and at the end of the game, the robot submits a map to the supervisor, and it grades it as a multiplier depending on the accuracy.
So our robot was designed with the following sensors. So we used, the sensors can be placed in a variety of locations, and some sensors some teams didn't even use. So sensors we used were the IMU to measure the rotation of our robot, the GPS to keep track of our position, and then the LiDAR itself just gives us helped us map the field with the help of the GPS and IMU to determine which areas we can explore. And then the way the LiDAR works is that it gives us an array of distance readings from hundreds of angles so that we know exactly where all the walls are at all times. Then we had 2 cameras at 64 by 64 resolution so that we could detect the hazards and victims on the walls. And we also had a color sensor to figure out what color tiles are on currently, and to avoid black holes, which if you drive into, your robot falls in, so you don't want that. And then our total cost was 2,950 out of 3,000. So this total cost, maximum cost, is like a limiter so that you don't like buy like 500 cameras or something. So so that the robots are like actually reasonable and something you can build in real life. And so we created this custom GUI tool to help debug our code and algorithms, and also to train our victim detection, which uses machine learning. So how we did this was we used a SDL2 to create the window, and then we used IMGUI and IMplot to draw the interface you see using SDL renderer. And we had a variety of tabs that you can see up on the screen to control different parts of the robot and debug various parts of the robot too. And then you see this like legend thingy. We could click each of these items to like disable them on the fly so that we can have a better like view of what we're actually trying to debug. So here's a demo of our UI. So So for movement, it's roughly based around a 1 centimeter grid. And we use PID control for both rotation and translation. So for translation, we cubed our error, which is target minus current, in our PID control loop, so that within only the last centimeter, before that, we would just drive at maximum speed. And then to ensure that we don't get stuck in a wall, we would just stop moving after 5 seconds and try to recalculate a path. Then for rotation, we took the square root of the error, which is the same thing, target minus current, to increase our speed. And we used a really low error margin for accuracy so that we don't need to use PID while driving as well, to maintain the head. So here's just a demo of why we use the cube and square root. So here you can see that our movement is pretty slow, especially on that last centimeter. And you can also see our turning is pretty slow too. And then with the cube and square root, you can see that we're significantly faster at both turning and moving in this small distance. So this is an important reason for why our movement is really fast. So for mapping, we use the SLAM algorithm to convert our LiDAR readings into a map. So what we did here was we took our current position and then the current point that we're seeing, and then used its angle to calculate its position relative to the world. And we would store these points into these 10 by 10 centimeter grids that you see here to make sure the algorithm's cheap, not cheap, but like it's computationally cheap. And it runs after every step to make sure that we have the most up-to-date map possible. So the data structure we used to achieve this was the unordered map, which is basically a big hash map of points of regions, and each region would hold a unordered map or a hash map of points, and it can store points in any arrangement so that we don't have to approximate the map, and so that we can fit into really tight spaces, which gave us a big edge in the competition. So some issues with the LiDAR and Weebots was that there was a lot of noise in the return distances. So to mitigate this, we put our max distance to 0.3 meters. And to prevent duplicate points, we would not insert points if there was another point within 0.0045 meters. And the noise was actually caused by 2 Weebots bugs, which have both been fixed in future versions of Weebots. And we also biased our distance readings from the LiDAR by negative 0.001 meters to prevent a robot from running into walls.
So some ways how our robot uses this map generated by SLAM. So the entire map is only accessible by the map bonus code, which we'll get into later. But we have some other wrapper functions to help interpret the map data. Is traversable takes in a point and determines if the robot is able to fit in that location without touching any walls. Midpoint check and can see do basically the same thing. They check if a straight line between 2 points can be driven by the robot, but they use different algorithms. And add LiDAR point adds a LiDAR point to the correct region, and it's used to add points calculated from SLAM for mapping and also marking black holes. So here's an explanation of is traversable. So it checks for points within a circle of the specified radius within the surrounding regions. It doesn't check every point because that on large images that would be very inefficient, because points far away, like there's no chance that they would be close to the robot. Midpoint check, it runs is traversable recursively between 2 points to check if a straight line between 2 points is traversable the whole way. And it also only uses neighboring regions. CanC does the same thing as midpoint check, but it uses vector math instead of is traversable to calculate the distance between the line between the 2 points and all other points in the surrounding regions. So for navigation, we decided to take a wall tracing approach because all victims are on walls, and those are basically the only parts of the maze that we're interested in. So we keep track of points that are next to walls. They're our main targets for navigation, and those are the green points that you can see in the image. And we also keep track of points that the robot has already been to, so we don't go to the same area twice. And visited points are counted by points directly to the left and the right of the robot, so like what each camera sees. So we try to see like every point on the wall to check for victims. And to help wall trace, we use depth first search on the grid of points. Depth first search is a graph search algorithm which goes the farthest it can along a branch and then backtracks. So the robot would check for points like all the way along the current wall until it finds a point outside a certain radius, and it prefers directions closer to the current wall. The current wall is defined by whichever side has the shorter LiDAR reading. Directions it would prefer are directly towards the current wall, and then the next would be diagonally forward and towards the wall. And it returns a stack with the points of the path found. For general pathfinding, we use breadth first search, which is another graph search algorithm, but instead of going down the first branch, it searches through points in the order of distance from the current point. And it basically finds the shortest path between 2 points when a straight line path is impossible. And unlike our other grids, it does not use a 0.01 grid because we ran into some issues with tight spaces that we'll get into later. And it also optimizes the path and returns it as a stack. So when DFS wall tracing failed, we had to switch walls, which we achieved using the nearest is on mall function, which uses BFS to find the nearest non-visited point next to a wall. And it basically just switches to the nearest wall that hasn't been visited yet, and it starts line tracing again from wall tracing again from there. So to optimize our movement, also we use a path optimizer, and here's an example of an optimized path which has a robot stop and turn at each point on the path. But after the path has been optimized, it gets rid of a lot of those unnecessary stops and also 90-degree angles, which are slow to turn. And black holes, they're basically just like holes in the ground that if the robot drives into, it just falls and you basically lose your progress. And there's a black border around the hole that we check for with the color sensor. And if the sensor detects black, the robot first moves back and then adds a square of points around the black hole, so the robot won't go there again. And this is a problem we had with BFS. So as you can see in that world, there's some really tight diagonals between curved walls and half tiles. So like this one right here, and also that one. And so, but because of how our LiDAR map worked, so and that the BFS grid was 0.01, the robot didn't think it could fit through the diagonal. So some spaces it couldn't reach if the only entrance was one of those diagonals. So we tried to decrease the grid spacing used by BFS to 0.005 meters, and it worked in most cases, but it still didn't work every time. So the full solution was so that when BFS couldn't find any more points to go to, it would sweep in a circle around the current point to search for points in an even denser grid, and it would also increase the radius if it couldn't find points close enough.
And the reason we did that was because by just using a really small grid, we would run into the problem where the code was just too slow. So that's why we did the circle approach.
To detect victims and hazards, we use OpenCV, which is a computer vision library, to process them. It checks for victims each step while it's moving and turning, and it uses the KNN algorithm to train the letters and black or white hazards. For the colored hazards, we had to use HSV, which is basically a color thresholding, and we use it to check for the red, and there's another orange contours and the area of these colors on the camera. For victims, to approximate the point, like where they are on the map, we used some trigonometry, and we get it within half a tile radius, and we emit it to the supervisor to get the points.
So here's a little bit of the math behind how we converted a victim to a point. So the camera output is like a matrix that just has pixels and rows and columns. And so we would get the offset in columns of the victim from the center of the frame. And then there's also, the matrix also has a total number of columns, and the percent offset from the center of the frame would be the difference in columns from the victim and the center divided by half of the number of total columns, which is the yellow line divided by the length of the purple line. And we knew the field of view of our camera was 1 radian, so half of it will be 0.5 radians. And so by doing some trig rearranging, we figured out that the angle between the straight line to the center of the frame and the victim was the tangent of the percent offset times the tangent of 0.5 radians. And so depending on which side the camera is on, the left or the right, is converted to an angle relative to the robot, which is then converted to an index in the wider range image. And that gets you a distance to the wall. And with that distance, the angle, and the robot position from the GPS, we could calculate the victim position and store it in a list.
So since we only have a 10 by 10 grid for our KNN, which is our machine learning algorithm that we use to detect the corrosive, poison, and HSV letters, we had to use adaptive and HSV thresholding to figure out the amount of black pixels in the victim, because otherwise the poison, which is mainly white, would only appear as like a white diamond. So we just used HSV thresholding to figure out the amount of black pixels. And then another issue we faced was with colored obstacles. So colored obstacles can sometimes be red and orange, and sometimes red and orange in the same frame. So then we would have to make sure that it is actually a victim and not just a colored obstacle. So how we fixed that was we used distance checks on the detected victims, and we would also compare the ratio of the areas to make sure that they're around 1-to-1, since the orange and red are around in a 1-to-1 ratio in terms of area. And then to prevent double detections, we used HSV thresholding once again, since adaptive thresholding didn't work, because as you can see in this detected victim up there, you can still see like the way it's gray, and the adaptive threshold is able to pick up on that and amplifies the contrast. So we use HSV thresholding to make sure it's black enough and to be an actual victim that's not been detected yet. And we previously, before using that approach, we used a victim position to check for duplicate victims, but that didn't work too well because the walls are double-sided, so it would think that it's already seen that victim because it's on the opposite side of the wall and has a really similar position, since the walls are only like 2 millimeters thick.
So to get the map multiplier at the end, the robot first gets its starting position at the beginning of the game, which is encoded over here using the GPS. And then it gets the dimensions of the map array by retrieving the minimum and maximum dimensions of the map, then dividing it by the size of the tile, and then rounded to get the map array dimensions. And then to check if there's a wall on a point, it just uses the is traversable function on the map array that we talked about. And then the map is subdivided into 0.303 times 0.03 meters. So, which is what you see here. Each of these numbers and letters are a vertex. For color tiles, we used color sensors to detect the colors, and we stored the tile positions using a map from the color to the position. And to debug, we use Erebus's debug mode to view the answer maps without having to do a full run, and then looking at our accuracy. And there was a problem where where the victim position would be off, like over there. It's supposed to be in the wall and not outside. And the shape of the curves, as you can see over there, we did manage to solve that because there was a problem with checking like the bounds for where the victims could be placed. So the victim ended up going to the extreme right and below of the map, even though it should not have been. For room 4, which is the non-tile based section of the world, we flood filled the matrix starting with one of the room 4's entrance tiles, and it would stop flooding if it would reach a non-room 4 tile or if it was outside of room 4's boundaries. And after that, the finished matrix would be submitted to the supervisor.
Alright, so we used to have some performance issues in older versions of our code. So what I would do sometimes was generate flame graphs like this. Basically what it shows us is like which parts of our code are taking up the longest amount of time. And to do this, I just found some random like GitHub repository which allowed us to generate like SVGs of the timing of our code. So here is an example of the good flame graph where most of the stuff is taking up a reasonable amount of time for what it's doing. And then here's an example of a bad one where we can see this arbitrary increment is eating up all of our performance. And the reason for that was because we used to use ordered maps which use a tree, and trees were a little bit too slow for whatever we're trying to do. So we switched over to the hashed version, so our unordered map, and that fixed a lot of our performance issues. So yeah, in the competition, our code name was RS92. So here are all of our field scores for each round. So each round has its own maze, and then we would run our code on that maze. And overall, if you can't read the number on the screen, we got 0.968 out of 1, and our time was 39 minutes and 56 seconds.
So at the end, after the main competition, we had a technical challenge where we had a limited amount of time to solve a problem, which was loosely based on the main rules. So like before, we would find as many victims or hazards as possible, but some of the victims or hazards could not be detected, as in if you detect them, you lose points. And each victim or hazard has a print statement associated with it. So when you detect one, you have to print something out to the console. The main challenge was that only victims or hazards on these floating tiles could be detected. And if it's not on a floating tile, it counts as a misdetection and you lose points. At the end, you could receive a multiplier if you print the correct number of each victims or hazards detected during the run. And if you get it correct, yes, a bonus is awarded manually by the judges.
And the technical challenge is worth 10% of the score, and we do not know of the rules until the day of the technical challenge, where we were given 90 minutes to solve the question. So what we did is we tried to initially maximize the amount of points we would get. So first we removed all of the unnecessary print statements and all the victims that are not part of the rules, because if you have unnecessary print statements, then they won't give you points for all the victims you do detect. And then we then printed out to the console all of the associated grocery items for every victim. And then we stored all of the detected victims in a map for the multiplier that we would get at the end. And then we removed the map bonus code because that is not allowed by the rules. And then now for the difficult part, we had to distinguish between the linear and floating tiles.
So in essence, a linear tile is just any tile connected to the border walls of the world. And floating tiles are just not connected to the border walls of the world. See here, they are labeled in green, and the linear tiles are all in yellow. We didn't know about this until later, but there was an exception where no matter about the connectivity of the world, the 8 tiles adjacent to the starting tile are all linear.
So our solution involved these 2 key observations. So if there's a top and bottom wall on the previous tile of our flood fill, then the tiles directly left and right to that tile would be linear. So if you look at the first map over there, you see like next to the start tile, there's a wall up here. So that means that the wall left to the left of that must be linear. Then the next thing we noticed was that the tiles, if there's a left or right wall on a certain tile, then the tile directly to the bottom or top of that tile would also be linear. So if you look at this tile, for example, then the tile, since there's a right wall here, that means the tile below it is linear. So with those 2 key observations, we built a simple flood fill algorithm.
So yeah, if there's a wall above or below the current tile, we just push the left and right tiles to the queue. And if there's a wall to the left or right of the current tile, we push the top and bottom ones to the queue. And we stop flooding at the boundaries of the maze. So in the end, the queue only contains all the linear tiles of the world. Since we don't use a tile-based system, we just use isTraversable to check for walls around a tile.
And yeah, this was our technical challenge score. It was a major contributor to why we won the competition, because we were originally going to be like 2nd or 3rd place because our documentation scores weren't great. So we recovered by our technical challenge score, which was extremely high. Yeah, here's the video of the 4th world at the international competition. It was just played in the background, and if you have any questions, please ask.
2 questions. Do you ever plan to build this robot in real life?
Yes, actually. So,
So robot simulators such as Weebots and many others are used by companies such as NASA and Lockheed Martin to test their products before they build expensive versions of them, so they don't waste a lot of money if it fails. And so right now we're planning to develop a plugin to simulate physical robot code in Weebots, which we can also build. So we can also build a version of our robot physically, and we can have it also run in Weebots as well.
So our code is also open source, and here's the link to our code. It also has some information about the hardware we used at the competition. I'll just leave it up for a few seconds so you guys can grab the links. So any other questions?
So that thing which you're showing, so you worked with that here before going to competition, or they give you a new set of? that rooms you're showing, right?
Yeah, so this is actually one of the ones at the competition. We got, they gave the link, they gave the roles, they uploaded them after we ran them on that day.
Oh, okay, so you need to your algorithm should work for any type of.
Yep. So we don't know the mazes beforehand.
Okay, got it. Okay.
What's your question?
Does the robot code does this Weebot software simulate the real life limitations? So can this actually be made feasibly and easily into a real product, into a real robot?
Yes, but we do have to make a couple of tweaks. The Weebot's GPS is incredibly accurate, which that's not something we have in real life. So in real life, we would have to use something called, you have to actually like simultaneously localize while mapping, and also use the odometry of the wheels, like the encoders, to figure out our position. So yeah, that's how you would convert that aspect into real life, but the rest of it is like identical. You can use the exact same code in real life.
So your algorithm, you can use some DSP, right, processing from the camera. You have some algorithm, you show how you calculate the tiles and, right? You can use some signal processing techniques, I guess, right? More advanced techniques there to detect accurately. Are you planning to add that or?
No,
refine?
actually, can I answer that really quickly? They're using LiDAR.
Okay,
LiDAR,
LiDAR.
right?
Okay.
LiDAR they're spinning and can do the mapping. So that what you said is not applicable in this case.
Oh,
Right,
okay.
so it's not that the technique is not hard. I'm sure if they want to pick up technique, I'm sure these fellows is really bright people who would pick it up, but it's not really applicable in this case.
Okay.
Yeah.
What's your question?
Why did you guys choose to do simulation instead of like maze or line?
Well, so I've done Line 2 years ago and Maze the year before, so I just wanted to do something new. Yeah. What about you guys?
I just didn't have time to come to the center every week.
I like it.
The advantage of that is that you can really drill down into the algorithms without being bogged down on hardware. That's it.
Yeah.
There's really no reason. As you can see, the hardware cost is pretty expensive, right? So literally, all you can afford is just buy your kids a nice computer and that's it. So it's just
Yeah.
no zero cost any other than that, right? So that is, I think, is a great opportunity for kids to learn about writing algorithms. But then, of course, if you want to actually get your hands dirty with like wiring, soldering, things like that, building a robot, then of course, then that would not be a good resource. However, still can a good resource to figure out the algorithm before you put it in hardware. That's exactly how all the strong arm companies doing. NASA do it. Of course, they have to do
Yeah.
that, right? NASA, I mean, they cannot get a satellite test in space, right? So everything is about simulation. All these strong companies like Lockheed Martin, Northrop Grumman, and then Boston Dynamics, they all do simulation first. So then that gives them opportunities to explore that, right? So that's good.
Building stuff will be done by robots.
Yeah,
Not by
probably
humans
too,
anymore.
right? Well, anyway, that's expensive proposition, so. Right, very good. Did you guys mention about SLAM?
Yeah, so basically what SLAM is it's a algorithm that takes the readings from a LiDAR, and since there's so many of them, you're actually able to combine them together to figure out your position and build the map at the same time. So that's basically, but since we had a GPS, we didn't extensively utilize it, and yeah, so we just basically took the GPS position and our LiDAR's readings and just fused them together to get our map. But if we were to do this in real life, we would implement an actual SLAM algorithm and use that to build the map. Anyway, so here's our final score. You got 2,236.61. This is the highest score that someone got at the competition.